Good day and welcome back to another part, I believe it's the fifth part now, for our discussion on maximum and minimum values. So in previous videos we've introduced the concepts of critical points and how we go about finding and classifying them. In this video we will extend a key idea from Calculus 1, something that we call the extreme value theorem, which I will almost always abbreviate as EVT. Now the Calculus 1 version is as follows. If f is a continuous function on a closed interval from a to b, so I'm thinking some arbitrary continuous function from a to b, then the conclusion is f attains an absolute maximum and minimum value on that closed interval from a to b. That is, there has to be some input that gives you an absolute largest output and some input that gives you an absolute smallest output. And by inspection, we can kind of see where that happens. We have the absolute minimum occurring at the left endpoint of A, and then in between A and B, there is a critical point, and at that critical point is where we will attain the absolute maximum. That is to say, these absolute max and min values can occur at 2 points. They occur either at a critical point or at an endpoint of the interval. And that will always be true for a function of one variable, which we will use at the end of our video in an example. So moving on and generalizing this to functions of two variables, once again I will almost always abbreviate EVT for the extreme value theorem. It tells us kind of essentially the same thing. If you have a function which is continuous on a closed and bounded set in R2, then f attains an absolute maximum and minimum value in D. And note kind of the similarity. The two big hypotheses. We need the function to be continuous, and we need it to be on a closed and bounded set. And note that this closed and bounded set is analogous to that closed interval from A to B. And the new concept here is just the idea of understanding what do we mean by a closed and what do we mean by a bounded set. And luckily these are very intuitive ideas. A closed set in R2 contains its boundary. And let me illustrate this with a few examples. So an example of something that would be closed would be a circle and everything inside it, because that contains its boundary. Or maybe a triangle or rectangular region, pick your favorite, and everything on the boundary and everything inside. Something that would be not closed would be to take either of these examples we have to the left and just remove a portion of its boundary. So for example, instead of maybe having the entire boundary or outside of that circle, if we remove some, it does not contain its boundary. So not closed. And luckily for us in here, we can approach this from a very intuitive perspective. Similarly, a bounded set in R2 is simply put one that we can draw a box around. And what we mean by saying we draw a box around it is that it does not grow indefinitely. That no matter what direction you go in, you always find kind of this boundary that it cannot go past, i.e. a bounded set. And the prime examples for us when dealing with the extreme value theorem will be things like circles and everything inside them, triangular regions, and then kind of rectangular or even parallelogram type reasons. These are the primary examples of closed and bounded sets. Now, in terms of finding these absolute maximums and minimums that we are guaranteed that the function will attain, we can approach this in a very nice procedural manner. And the nice thing is it's the exact same approach we used back in Calculus 1. So the first thing we need to do is find the value of the function f at each critical point inside that region of interest D. If the critical point is not inside D, then you simply throw it out and you are unconcerned by that critical point. The second thing you do is you find the extreme values of f on the boundary of D. And for each part of the boundary, when you're searching for these extreme values, think absolute maxes, absolute mins, these are calculus 1 problems. So you will have multiple calculus 1 problems. That is to say, this procedure is going to be, somewhat tedious, as we'll see in our next example. Once you now have this list of values, the values of f at each critical point, the extreme values of f on the boundary of D, this has built up for you a list of values. The absolute maximum and absolute minimum is just the largest and smallest respectively. So the largest value is the absolute maximum, and the smallest value is the absolute minimum. And we are now ready to explore an example. This is a very typical application of the extreme value theorem. Find the absolute maximum and minimum values of some function on some region D. Let's go ahead and really break this down. Let's first sketch the region D and make sure that it's closed and bounded, and also verify that the hypotheses of the extreme value theorem are satisfied. So in terms of the region D, what is being described tells us we have all points of the form x comma y, so points in the xy plane, where the x values go from 0 to 4, and the y values go from 0 to 5. So 0 to 4 in the x direction, 0 to 5 in the y direction. So what is being described is a rectangular region. And the observation that I want to make is D is closed and bounded. Also, we can note that the function f is a polynomial in 2 variables, and as we discussed earlier, that means it is continuous. So f is continuous, we could say on D, but I'll go ahead and just say on R2 to make it an even more general statement. And the fact that D is closed and bounded and f is continuous, this implies that the hypotheses of the extreme value theorem are satisfied and we are able to apply it. So if we go back to our procedure on the previous page, in order to apply the extreme value theorem, we are going to make a list of possible values to play the role of the absolute maximum and absolute minimum values. And from that list, we will pick the largest and the smallest. So the first thing we need to do is find the critical points of our function. So the partial with respect to x is 4 minus 2x. The partial with respect to y is 6 minus 2y. A critical point occurs only when both of these partials simultaneously equal to 0. The first implies that x is equal to 2. The equation from the partial with respect to y tells us that y is equal to 3, which means we have a critical point at 2, 3. And we are interested in this critical point as long as it lies in our region D. And 2, 3 lies right in the middle of our region D. So we are interested in the value of the function at 2, 3. So I'll try to keep my list of possible values to the right so that we can easily pick off the biggest and smallest for our final step. So the first value on our list is the output of 13 associated with this critical point at 2, 3. The second part of the extreme value theorem from a procedural standpoint is we need to know what are the absolute maximum and minimum values along the boundary of D. So that would be around this rectangle that makes up the outside of the region D. And the best thing that we could possibly do here in terms of approaching is break it into pieces. So I'm going to kind of enumerate the sides. We'll say A, side B, side C, side D. And unfortunately, we're going to need to go through and do a separate calculus 1 problem for each of the 4 sides of the rectangle. And let me repeat that and let it sink in. We need to do a separate Calc 1 problem on each side of this rectangle. So let's start with side A, and what we need to do is describe it. Side A is made up by the line segment, y equals 0, with the x values being restricted between 0 and 4. So we are simply describing this bottom of the rectangle. Y is 0, as in this line segment, specifically from 0 to 4. And what we need to know is when we substitute this information into our function f, what can we say about maximum and minimum values? So we replace each y with a 0, and we end up with 4x minus x squared. And we need to know as x varies from 0 to 4, how big and how small will the function be? And note, as that is a continuous function on a closed interval, this has reduced down to the calculus 1 version of the extreme value theorem. And what the calculus 1 version of the extreme value theorem tells us is that those extreme values of interest occur at one of two types of points: the boundaries of the interval, i.e. 0 or 4, or a critical point in between. So if we differentiate to find the critical points, we would end up with 4 minus 2x, and a critical point occurs precisely when that quantity is equal to 0, which means x is equal to 2. And that's our single critical point. And this allows us to determine 3 possible points where you can have extreme values. You can have an extreme value at the endpoint, so when x is 0, and we already said y is 0, or when x is 4. And then we have a critical point when x is 2. So note, in the middle, this is corresponding to the critical point, and on the outsides, this is corresponding to the endpoints. And the associated values would be that f of 0, 0 is 0, f of 2, 0 is 4, and f of 4, 0 is also 0. Now, we've played this game once on the bottom. We need to also find the extreme values on the right side, the top, and the left side. That is to say, we need to repeat this game 3 times. And by calling it a game, maybe I can convince you that it's fun. So on the right side, that would be the vertical line x equals 4, but only the portion of that line between 0 and 5. And if we substitute into our function x is 4 and leave y as is, this would give us back 6y minus y squared, because the x terms cancel off when x is 4. And what we would like to do is once again apply the calculus 1 version of the extreme value theorem. So we need to find the critical points. We differentiate 6 minus 2y, and this would be equal to 0 only when y is equal to 3. And we now have 3 more potential spots where we can have an extreme value. So we have x is 4, and what we need to check are the endpoints. So the endpoints corresponding to our interval would be when y is 0 or 5. And we can also have an extreme value at the critical point, which corresponds to y equals 3. So f of 4, 0 is equal to 0. F of 4, 3 is 9. F of 4, 5 is 5. And I'm running out of space a little bit here, and maybe your patience as well. So what I'm going to go ahead and do for the next 2 parts is I'm just going to write down a description of the side and note that a similar type of analysis will work. And I've now included a few details. We have to take care of the top and the left-hand side of the rectangle. So along the top of the rectangle, we would describe that side C as a portion of the line segment y equals 5, particularly with the x value ranging from 0 to 4. So if we substitute that information in, do a calculus 1 problem, we find the critical point occurs at x equals 2. which means we can have a maximum or minimum type of behavior at that critical point in the middle of the endpoint interval, or at one of the intervals. And those gives us the values 5, 9, and 5. Similarly, on the left-hand side of the rectangle, which corresponds to x equals 0 and the y values from 0 to 5, you have the endpoints of 0, 0, and 0, 5. And I've left out the details once again, but I think you all can fill those in, and I would recommend it as good exercise. There's a critical point when y equals 3, and the associated values are 0, 9, and 5. And we are now to our final step, which we can hopefully complete purely by inspection. We want to look at this list of values that we have. That is all of these associated outputs along the boundary of the rectangle. And then I'm going to scan up just a little bit to also include the function value at the critical point. Now remember, the absolute smallest number we see in this list would correspond to an absolute minimum, and the absolute largest that we see would correspond to an absolute maximum. So note the minimum occurs at two possible inputs, 0, 0, and 4, 0. And the maximum occurs at the critical point, 2, 3, that lies inside the region. And because there's so much going on with these problems, a very important step is to summarize. So an absolute minimum occurs at 0, 0, and 4, 0, with an absolute minimum value of 0. An absolute maximum occurs at the critical point 2, 3, with an absolute maximum value of 13. So a very important part is to summarize all of this fantastic work. At what points do we attain the absolute minimum and maximum, and what are those associated values? So as I've mentioned, these are somewhat lengthy and tedious problems, so this is a great opportunity to practice. If you go to Canvas, you will find a worksheet associated with maximum and minimum values that will give you a great starting point. In fact, we will have one more video left on this topic where we will go over the first problem on that worksheet. So stay tuned and take care.